Welcome to Maths with EJD. This is actually a continuation of the video on eigenvalues and eigenvectors. I was able to treat a problem, a 2x2 matrix in the other video. I was able to find the eigenvalues and eigenvectors. So now I was starting out with this 3x3 matrix and something came up, so I couldn't continue with that. So this is a continuation of that. So I'm just going to focus on getting the eigenvalues and eigenvectors of this 3x3 matrix A. All right. So the characteristic equation, like we know, is A minus lambda I equals 0. And like you know already, this is our A, right? Then minus lambda I. So for 3x3 matrix, you just have lambda 0, 0, 0, lambda 0, 0, 0, lambda. And that is 4 minus lambda. You have all of that going on along the principal diagonal. So 4 minus lambda all the way. And you have 1 minus 0 everywhere. So you have all that going. So the next thing now is to find the determinant. The determinant of all this. So, of course, by now you know how to do that. You have 4 minus lambda. First, you assign values. You have plus, minus, plus, right? So you have 4 minus lambda into, when you cross this and you cross this, right? So you have 4 minus lambda into cross this column, cross this row. So you have 4 minus lambda times 4 minus lambda. That's like 4 minus lambda squared. Then minus 1 times 1. That's 1. And the next thing is minus 1. You have minus 1. Okay. So, this is plus again. So now you have minus 1. So that's minus 1 into cross this out and cross this out. So you have 1 times 4 minus lambda. So you have 1 times 4 minus lambda. That's 1 times 4 minus lambda minus 1 times 1, which is also 1. And then you get rid of all this again. And you have plus 1 into cross this column, cross this row. So you have 1 times 1, 1, minus 1 times 4 minus lambda. So you have 4 minus lambda. And all this is equal to 0. All this is equal to 0. So if you tidy all this up, right, you see you're going to get 4 minus lambda, right, into this now. You can do the fast way. Square the 4, that's 16. Then 2 times 4 times 8, that times lambda, that's minus 8 lambda. Then squared minus lambda squared, you have plus lambda squared there. Of course, minus 1. So that takes care of all this. Then for this next one, you can just keep this. You have minus 1 times 4 inside, that's 4 minus 1 times minus lambda, that's minus lambda. Then this minus 1. So you have this minus 1. And here you have plus 1 into 1 minus 4 plus lambda. 1 minus 4. Minus times minus is plus lambda. And all this again is equal to 0. So you can get rid of this. That's us trying to resolve all that. Now, we've done so many examples about determinants in the past. That is why I didn't bother putting it in this document again. But I'm trying to explain in case this is your first time of encountering this, or or just to refresh your memory. Okay, so with this now, we have 4. I guess I need to change the color. So now we have 4 minus lambda into now 16 minus 1, that's 15 minus 8 lambda plus lambda squared. All right, that's for that. Then this next one, you have minus into 4 minus 1, that's 3 minus lambda, 4 minus 1, then minus lambda. Then lastly, you have plus 1 into 1 minus 4, that's minus 3 plus lambda. And all this is equal to 0. Okay, so now we can still keep tidying things up here. We have 4 times 15, that is 60. 4 times minus 8 lambda, that's minus 32 lambda. 4 times lambda squared, that is 4 lambda squared. And then here we have minus 3 plus lambda. And here we have minus 3 again plus lambda. And all of that is equal to 0. So we can, okay, I think I skipped something. So 4 times lambda squared, that should be 4 lambda cubed, sorry. So 4 times this is 60, 4 times this is minus 32 lambda, 4 times lambda squared is 4 lambda cubed. Okay, let me go back to that. I think I skipped something. I skipped something. That shouldn't be. So let's take that again. So 4 times 15 is 60. 4 times minus 8 is minus 32 lambda. 4 times lambda squared is 4 lambda squared, not 4 lambda cubed. 4 lambda squared. And minus lambda times 15. That's minus 15 lambda. Minus lambda times 8 times minus 8 lambda. That's plus 30 plus 8 lambda squared. The minus lambda times minus times plus lambda squared, that's minus lambda cube. Okay, yeah, that was what I skipped before. So I have minus 3 plus lambda, then minus 3 plus lambda again equals 0. So here, minus lambda cube comes. So you have minus lambda cube. Okay, let me color code that too. Or better still, let this go so we can have some space. So we just keep tidying things up until we get the characteristic equation, which we solve to get the eigenvalues as expected. Okay, so I changed the color again. So now we have minus lambda cube. That's the biggest one. So we have minus lambda cube. The next thing we talk about lambda squared. So we have 8 lambda squared and 4 lambda squared. That's plus 12 lambda squared. Then the next thing will be the lambda. So we have minus 32 lambda, right? Minus 32 lambda plus, minus 15 lambda. That's minus 47 lambda. Minus 47 lambda plus lambda, that's minus 46, plus another lambda, that's minus 45, minus 45 lambda. And then let's talk about the constants. We only have 60 minus 3 and minus 3. So 60 minus 3 is 57. 57 minus 3 is plus 54. So all this equal to 0. So of course, it's just logical that if we multiply this through by minus, we get what we have here. Because minus times minus lambda cube is lambda cube. Then minus times plus 12 lambda squared is minus 12 lambda squared. Minus times 45 lambda is plus 45 lambda. Minus times 54 is minus 54. And all of this is equal to 0. Okay? So that's how we get the characteristic polynomial. So the next thing we need to do is to solve this. So to solve this, of course, we need to use an array of methods, right? We need to use an array of methods. First of all, we have to check which value we go through and things like that. And I think I've done that in the previous example. So that helps. So we need to solve this. But on solving all this, right, I won't go through all that process now because this is a cubic expression and we have to do trial and error methods, But at the end of the day, you try, I think I did it in one of the previous questions. You try lambda equals, okay, I think I'll look for the video where I did that and I'll put it in the description so you can follow what I did in that place so that we don't take time on this. Okay, so when you solve all this, in short, you're going to get the 3 eigenvalues. Lambda 1 is 6, lambda 2 is 3, and lambda 3 is also 3. So here now you have repeated eigenvalues. So you have a unique one, which is 6, and then the other 2 are repeated. So we can treat those 2 together. Of course, one thing you must understand is that even though we have repeated eigenvalues, we must not have repeated eigenvectors. You can always make decisions because I've always told you the eigenvalues must be unique, but eigenvectors do not have to be unique. And I'm going to show you this as we take care of this question. All right. So now we have the 3 eigenvalues sorted. So the next thing is to find the corresponding eigenvalues to each one. So for the matrix so now our matrix A with eigenvalue lambda 1 equals 6. So lambda 1 equals 6 now. So again, you have A minus lambda I1. So the original matrix, don't forget, is 4, 1, 1, 1, 4, 1, and 1, 1, 4, like that, you know. So you have, so A minus lambda 1 would mean you have this minus 6, 0, 0, 0, 6, 0, 0, 0, 6. And that's why you have 4 minus 6 along the principal diagonal. And every other place remains what it is because it's just that minus 0. So everywhere you have 4 minus 6, you're going to have minus 2 all the way. So you have minus 2, minus 2, minus 2, and then you have 1 elsewhere. So in this case, since you're dealing with a 3 by 3 case, so it means that the vector, the eigenvector can be taken to be x, y, z, and it is the vector that corresponds to lambda 1. So if that is the case, we have a minus lambda 1I times v1. So this is a minus lambda I1, which we got here, and this is v1, and all of that is equal to 0. And of course, you can already see that minus 2yz, 1 minus x minus 2yz, then x plus y minus 2z, like that. And that is exactly what we are going to have on the next slide. That's what we have on the next slide. So let's go to slide 11, where that is. Okay, so still on that, right? So just like what you saw there, if you turn all of that over, this is what you get. You get minus 2x plus y plus z equals 0, x minus 2y plus z equals 0, x plus y minus 2z equals 0. Now, well, you can, so in this case now, you can see that all the expressions are different. But one technique I always like to use is this last z, and I like to make it the subject, just like I made y the subject the other time. So if we make z the subject here now, what do you get? 2x comes and it's positive, so you have 2x. Y comes and it's negative, so you have 2x minus y, and that's why we have this expression. Now you can also do this for this other two. Now, so doing this 2x minus y. Now you discover that any other one you choose, say you also choose, if you can even choose x or y, anyone you choose, you always get the same value, 1, 1, 1. You know, if you pick one for both. Look, I mean, okay, let me just do this, right? So what we're just doing here is we say x is equal to 1 and y is equal to 1. So if x is 1 and y is 1, so that's 2 minus 1. So z is also 1, and that's why we have the eigenvector. So any non-zero scalar multiple of v1 is an eigenvector corresponding to lambda 1. So it means you can change, if you take 2, 2, 2, 3, 3, 3, 4, 4, 4, minus 4, minus 4, minus 4, any scalar multiple of this is an eigenvector, of course, of that matrix. So you know, like that. So if you make this one the subject, maybe you can even choose to make x. So if you make x the subject here, right, you have that'll be 2y minus z, and then you pick y, and y equals z equals 1, right? Automatically x will also be 1. So you see, it's also still corresponds to 1, 1, 1. So so in this case, anything you make the subject, as far as you pick the values of the first two as 1, you will always get that. So it's always advisable that you pick, before you do anything else, pick 1, 1 first and get the third one. So, but then and then the other eigenvalues don't have to be exactly the same as this. So you have to alternate, because there are many options you can have, as you're going to see when we do the other one. So next, we are going to have a repeated eigenvalue, which is lambda 2, which is equal to lambda 3, and that is actually 3. All right. And so for the eigenvalue, lambda 2 equals lambda 3 equals 3. So we look for this again, a minus lambda 2i, which is the same thing as a minus lambda 3i, which is now going to be 4 minus 3, 1, 1, 1, 4 minus 3, 1, 1, 1, 4 minus 3. And then you have 1, 1, 1, 1 like this. And then we go on to tidy all that up. So if we say v2 and v3 is x, y, z, are the vectors corresponding to lambda 2 and lambda 3 respectively. So we have this expression, and that will be 1, 1, 1, 1 into x, y, z equals 0. So naturally, you just see that is 1 times x, 1 plus 1 times y, 1 times z. And that's the same everywhere. So you have x plus y plus z, x plus y plus z, all that equals 0. So you don't need to even worry about anything. Just pick one, and you can make your decisions based on that one. But see what is going to happen here. Just like I said, the fact that the eigenvalue is 3 repeated twice does not mean that the eigenvectors have to be the same. So from x plus y plus z equals 0 now. And just like I told you, my method is to make the last thing, the one at the one at the last part, I just make that into z, and that is equal to minus x plus y. Z here, okay, maybe I shouldn't jump. So z here will just be minus x minus y, and that is the same thing as z equals minus x plus y. And what do I do? We've already taken x and y to be 1. So now what I'm going to do here is I take x to be 1 and I take y to be 0. If I do that, then z will be minus 1. And that is why I have 1, 0, minus 1 here. Then the other thing I alternate is I take x to be 0 and I take y to be 1. So if I take y to be 1, that means z again is equal to minus 1. And that is why we have 0, 1, minus 1. Now you have so many other options, right? You have so many other options. You can take, of course, you can actually take both again to be 1. So you have 1, 1. So that'll be 1, 1 minus 2. 1, 1 minus 2. That's possible too. You can have in fact, you can make x the subject again. If you make x the subject, that's be minus y plus z, right? So if you take y to be 0, and z to be 1, so that means x itself is going to be minus 1. So another possible eigenvalue you need is minus 1. That's x is minus 1, y is 0, and z is 1. So minus 1, 0, 1 is also a possible eigenvalue, all right? Though it's not exactly the same like this. So, but the thing is, any logical one you can come up with is good enough. So somebody else can do this and have one of the eigenvalues to be minus 1. In fact, for this particular case, 3 students can solve this problem and get the different eigenvalues, which through the same logical means. So though the eigenvalues are unique, the eigenvectors do not have to be unique, okay? So in fact, it's better to have the eigenvalues varied, because you have so many possibilities. So you just pick 2 that are, you make sure that all the 3. So you can see that V1, V2, V3 now are not the same. So you have 1, 1, 1 for V1. V2 is 1, 0, minus 1. And V3 is 0, 1, minus 1. So that's for lambda 2 and lambda 3, which are actually 3. So, I mean, you have to make that decision that way. So with some practice, you can actually get used to this. All right. So that's really important. So how you go through solving all this. Okay, so let's go to the last slide. I think the last slide is just about some exercise that you can try your hands on. Let's see that. Okay, so some practice questions right here for you. Find the eigenvalues and eigenvectors of the following. P equals 4 minus 5, 2 minus 3, and Q is 4 minus 5, 1, 2 minus 3, 0, and 1, 2, 6, like that. This key is going to be a bit complicated. Maybe you get square root or something there, or some decimal. So feel free to play with that. But don't forget, it's always very good if your x is first of all 1, and then it can decide other things. All right. So thanks for listening. See you in the next video.